Good evening, everyone. Thank you for joining this session. Sandeep and I will be taking this session. Of course, Sandeep's going to be taking the majority of it. We're going to be discussing MapReduce programming and its impact, especially immediately in the Savan project, whose problem statement has been released on the platform. So make sure that you take as many notes as you can from this live session, and I hope it's beneficial for everyone. Sandeep, you can take it away.
Okay. Yeah. Good evening, everyone. Glad to see all of you back on another live session. This time on MapReduce Programming, which is probably one of the, I would say, a challenging module because of several reasons. One, that this is the first time that you will be probably doing distributed programming. Really, I mean, you will be implementing distributed programming, and secondly, most of all the coding that you will be doing here is at the low level, that is using simple Java or Java APIs. And as we move forward in the next courses and so on, we'll be introducing you to several abstractions which are built on top of MapReduce. So this is one of the few low-level, tools that you will be studying. So apart from this, Spark RDD is probably one more, and Storm will be another thing where you will be working at the lower level, but most of the things are built on top of these things. So just to give you a brief or quickly recall from where we started, and then I will just run through this module, and then probably give you some idea about what lies ahead, in particularly for the Savan MapReduce project, and then we'll have a discussion around it. So I would like to take you back to the module in course 2 where you did algorithm design using MapReduce, right? So over there you learned that there are these two constructs with which you can actually do a lot of distributed programming. I mean, it actually makes your life much easier because of these two constructs. The first construct is a map construct, and the second construct is the reduce construct. So map essentially divides or parallelizes, and you can actually work on each split of the input data in parallel, and you produce an intermediate output. And then there is what the framework does for you is that it essentially ensures that the intermediate output is grouped by a key. Okay, so all the values which are corresponding to a single key go to the same reducer for further processing. And in the reduce stage, what you essentially do is all the aggregation which you need to do, you write a function for that, and it does the aggregation for you. So you saw that many of the problems can actually be solved with this simple map and reduce concept. The first example that comes to your mind is, of course, the word count problem, right? So counting words, the simple way to do it is in the map, you for each word you write a key value pair corresponding where the key is the word, the value is the constant equal to 1. And in the reducer, what you need to do is, like, for each key, which is your word here, you add up all the ones which come along, okay, thereby obtaining the frequency count of each word. So this is where we started off in algorithm design using MapReduce, but be very careful that in algorithm design module, although in the later part we did mention about key value pairs and other things, we never mentioned anything which was particularly specific to Hadoop, right? In fact, the motivation of that module was to say that, see, here is a framework which provides you two constructs, a map and a reduce, and using which you can actually do a lot of distributed programming, or you can actually implement a lot of distributed algorithms with ease. Okay, so this was the whole purpose of that module. Now, which means that several frameworks or various frameworks can implement this MapReduce paradigm or the algorithm model in different ways. Okay, and Hadoop implements it in its own way, and hence its set of libraries are also known as MapReduce. Okay, so specifically, if you want to talk about this module, that is MapReduce Programming, it should have been called Hadoop MapReduce Programming, because we are now restricting ourselves to the Hadoop way of doing MapReduce. You will see later when we go to Spark, Spark also does MapReduce, but Spark has its own way or its own libraries to do the same. Okay, and moving even further, even in real-time processing, you will see or realize that most of the things that you will do are actually using the MapReduce algorithm or the MapReduce paradigm. But of course, the way in which you implement the map and the reduce will be different from how it is done in Hadoop. Okay, so with this very brief introduction, let me just quickly run you through the module of this particular module, that is MapReduce program. So let me share my screen so that you have something to look at. So I hope my screen is visible. Okay. Yeah. Now, so you can see that the MapReduce, I have just opened up the MapReduce programming page, and the first session of this particular module is where we are introducing you to the Hadoop MapReduce framework. And I would like to make a note here that please do not get confused. Previously also I have seen some students asking the question that, is this referring to Hadoop 1 or Hadoop 2? What I would like to say here is that this should not be thought about as 1 or 2. It is simply the way Hadoop actually implements MapReduce. Okay, so which means that we are not bothered about how each mapper and reducer is implemented in the Hadoop framework, but rather simply what are the steps, okay, what are the steps which are involved in implementing a MapReduce program on Hadoop. Okay, so that will always be the same. Of course, there will be changes in how a mapper or a reducer is being taken, whether it is a job tracker or whether it is a application master which is taking care of all these things. That is more related to job monitoring and things like that. We are not getting into that territory. You already know how those things are done. You learn that right upfront in this particular course. So here we are just going to stick to how Hadoop how Hadoop implements a MapReduce program. And we use a simple word count example, and we show you that how you write a map function, and based on the map function there will be intermediate key value pairs. On this intermediate key value pairs there is a grouping by key, and how partitions are formed and how the sorting is done, and all these things. And in between you can very well have a optional thing called as a combiner, which essentially aggregates all the intermediate key value pairs which are on each mapper. Okay, so it is, I would say, a local kind of a grouping, okay, which is done by the combiner. And of course, after this, there is for each key, all the corresponding values are grouped by and sent to the same reducer. And that part is, of course, then the reducer will implement the reduce function which you have written, and you will get the final output. Okay, so here, what we would like to mention here is that this process, that is, there is a mapper, there is an optional combiner, and then there is a reducer. So this is something which you have seen previously. So what we have done here is like, okay, given some more details about how these things happen, particularly with respect to Hadoop, where everything happens in the form of key value pairs. Okay. Now, finally, we also talk about job scheduling and fault tolerance, which is an overall, I would say, an architectural view, again, without taking much into consideration of whether it is Hadoop 1 or Hadoop 2. It is more about how this framework, in order to provide fault tolerance, how it actually goes by. So, for instance, it's as simple as if there is a map task which fails, then what does it do? should it actually restart all the processes which were restart only the tasks which were presently running? The answer to that is it has to essentially restart all the tasks which were running and which were completed by that map task, due to the simple reason that the intermediate output is actually stored on the local file system. It's not put on HDFS. So you do not have a copy of it. So the only way you can do it is to replay or to start everything on that particular map task. Okay. However, if a reducer fails, then you are safe, because all the tasks which were previously processed by the reducer were put on HDFS. That is, the final output is always put on HDFS. So you have a replica. So even though a reduced task may fail, all that you need to resume or to restart is the task which were presently running on that particular reducer. Okay. So these are certain things which we have given here, and then you will see that even the questions which are asked, they are slightly at a challenging level, essentially because till that point we are not yet into programming. Okay, we are just giving you an idea, or at the pseudocode level, how the mapper and the combiner and the reducer work. It's only from session 2 where we get into the proper details, like how exactly, what are the different libraries that MapReduce or Hadoop provides for you to implement a program. And like every other programming language, here also we have followed the same thing. That is, first of all, when you start learning a new language, you want to know what are the data types which are supported by that language. And hence we have told you that what are the, in some sense, why there is a difference between the usual Java data types and the data types that you will encounter in MapReduce. And there is a very solid reason for that. The simple reason is that in MapReduce, we need to do a lot of data transfer. And in order to do a lot of data transfer, it's always better if we can serialize and deserialize things very efficiently, right? So any data type, when you are sending it over a network, you need to convert it into a stream of bytes, and that is known as serialization. So this serialization should not be as heavy as it is in Java, because we have constraints, we are transferring gigabytes and petabytes of data. So that's why we want to have a live serialization and a live deserialization, because of which we use certain specific classes for MapReduce, like int writable, long writable, text, and so on. Similarly, there are we explained to you about the various input and the output formats. Okay. And then we also tell you how to choose the number of mappers and reducers. So this is again a very important task, that how to choose the number of mappers and reducers. So in short, it is like you do not have direct control of choosing the number of mappers for a program. In fact, it's a good thing that the framework doesn't allow you to choose the number of mappers, because if you were allowed to choose the number of mappers and if you choose a very large value, then you never know the memory requirement for having so many number of mappers. It may not be even possible. So in other way, what the framework allows you to do is it allows you to specify the input split size. Okay, so in which indirectly is like choosing the number of mappers. So here, what you do is the default input split size is of course whatever is the default block size on HDFS. But you have the option to vary it. So you can specify a input split size which is less than the default block size, thereby increasing the parallelization. But you should also keep in mind that there is a time which Hadoop takes to set up all these number of mappers, and hence it is not a great idea to choose the split size too low, and it is not a great idea to keep it too high also, because if you keep it too high, then what happens is then the mapper will first have to transfer another block from another part of HDFS, which may be another node. It will first have to transfer that block to this block, and then it will have to run. So it will take its own time. So hence, in general, for most purposes, you go with the default block size, unless and until you are very sure that I want to increase the parallelization and so on. As far as reducers are concerned, the thing is generally like there may be multiple cases. Like for example, you know that each reducer produces its own file, it writes its own file on HDFS. So you may very well, the problem itself may be so naturally asking you to have multiple files for your ease. So in such cases, it's always better to have multiple reducers. But otherwise, most of the purposes, a single reducer suffices. Unless and until you are very sure that, okay, my reducer will write, let's say 5 input blocks, okay, 5 blocks of data. So then in such cases, maybe you can go for 5 reducers. But this is something which is not, again, most of the cases, a single reducer suffices. Then we actually get into the MapReduce API, which is essentially all the code which you will see in the driver class of a program. You will have to specify what is the input type, what is the key type, what is the value type, and what is the job name, and so on and so forth. All the things it provides you with a set of APIs. So all these things are explained over there. Then we get into proper mapper and reducer classes. So how to write the map function and how to write the reducer function. In fact, there is also the option of providing a combiner. And the best part is that you can very well reuse the reducer class which you have written as the combiner, provided you know this very well, that the reduce function should be commutative and associative. Okay. So in other words, the order in which the aggregation is done should not be a factor. If that is the case, you may very well reuse the reducer class itself as a combiner. If not, then you may have to think about it and come up with a useful combiner class. Okay. So we have given you a few examples, even in the case in the previous Hadoop MapReduce framework itself. We have given you a very interesting scenario where you have to compute the average word length, and how can you cleverly make use of the combiner in such cases. Because averaging, if you have take a look, it is not an operation which is commutative and associative. So you will have to cleverly make use of the combiner. But for most other purposes, like for example, whether it be addition or multiplication, these are operations which are commutative and associative, and hence you may very well reuse the reducer itself as a combiner. Now, then finally we get into the deployment of a MapReduce program on cloud, which is very important, and hence we have provided you resources with how to run a MapReduce program on CDH. So basically what you, there are multiple ways to do it, but something which is very useful or very natural to do would be to write your code on an IDE like Eclipse and package it as a jar file and transfer the jar file onto your EC2 instance using a client like WinSCP and just execute it on your EC2. So all the things have been provided to you, how to do that. And then what we did is like, okay, for so these if you look at it, MapReduce programming, one is we have introduced MapReduce programming using the simple word count example, because that is one example which essentially gives you, or using that example, we can explain almost all the features and APIs of MapReduce. In MapReduce programming 2, what we have done is we have provided you with a few examples and a few components which are particularly important. So the first thing is of course a partitioner. Okay, so the partitioner is again an optional component only. What happens is there's a default partitioner inside MapReduce framework, which is known as the hash partitioner. And as expected, what it does is like it ensures that all the key value pairs corresponding to a single key are sent to the same reducer. Okay. And how it does it using a simple hash function, right? All that you need to do is like you use a hash function, you provide the key to the hash function, and the output of the hash function is the number of the reducer. Okay. So every time a key value pair comes with the same key, it is sent to the same reducer. So this is done by the default partitioner. But several times what may happen is that the partitioner, or rather you may want to partition your intermediate output in a way which satisfy or which which achieve your objectives, right? So for example, we have given you a demonstration wherein you are given the server logs, okay, and you are given server logs, and what you want to find out is you want to split the entire server log, which is for 1 year, into months, okay. So what we are interested in is to have 12 files, each file containing the server logs for each month starting from January to December. And also we would like to see from each IP address how many times we got requests, okay. So it will be like 12 files, and in each file there will be an IP address followed by how many times we got a request from that IP address in that particular month. So this is a problem which is very natural to have 12 output files, one for each month. And in that case, it becomes very useful to make use of a partitioner, because you want to specify in the framework exactly where each record should be processed, right? It shouldn't happen that you may very well have 12 reducers. You can define 12 reducers to be there, but still you don't know whether all the records corresponding to January will go to reducer number 1, all the records corresponding to February will go to reducer number 2, and so on. So that is a rule which you will have to enforce, and the partitioner is the component or the class which allows you to enforce that rule in Hadoop MapReduce. Okay, so that's what we have explained it here. Then moving on to the next type is the custom data type. So this is very important. So whatever, like any other language, you only have a few basic data types like int writable, long writable, you have text similarly. But most of the cases you may have to come up with your own custom data type, just like how you define your own classes in Java for objects of a required type, right? So similarly, in this case, in this scenario also, you may have to define custom data types, and that is a tricky part which you will have to understand very well. And the reason why I'm calling this custom data type a bit tricky is essentially because it is unlike Java, where you can just define a class on your own and specify the fields and methods in it. Over here, there are some constraints which you will have to satisfy. The first constraint is that whenever you're defining a class, which is essentially like defining a data type, you will have to first check whether you're going to use it as a value or as a key. If you're using it as a value, then you will have to implement something known as a writable interface. Okay, and the writable interface is essentially because you want Hadoop to use the serialization and deserialization procedures which it has for its base classes. You want to use the same thing for your custom data type also, so that Hadoop can actually process it efficiently. So that is simple. So when as far as the data type is a value, you only need to implement the writable interface. So there are a few methods in it. You will have to define it. All these things are explained. But if you want to use the data type as a key, then there is something more which you want to do. You want to tell Hadoop exactly how you can compare two objects of this data type. And why do you want to compare two objects of this data type? It is because you are using it as a key. And in Hadoop, you know very well that there is a shuffle and sort phase between the mapper and the reducer. And the shuffle and sort phase, you know very well, it's like sorting the keys. So whenever you define a new data type and you are creating an object which will become a key, then you should tell Hadoop, okay, I have keys K1 and K2 of the newly defined data type. Then how can I say K1 is less than or equal to or greater than K2? So you need to define that rule. And the way you define that rule is by implementing the writable comparable interface on Hadoop. Okay, so you will have to define a few more methods on to implement this particular clause. So custom data type is that, and then we also encounter something called as counters, which are map only jobs. And counters in short are used whenever you want to get some simple statistics from your data set. So it need not be like let's say I have a huge list of documents, and all that I'm interested in is, let's say, I want to find out how many times 5 words, let's say something words like and, so, the, something of that sort, 5 words, I want to count their frequencies only. I don't want to count all the frequencies of all words. Then in order to do such simple statistics, what you can do is you can very well use the feature which is provided by MapReduce to have a global counter. So global counter, I'm very sure you did this part in the algorithm design using MapReduce assignment, where you had the provision of a global counter and a map only job actually sufficed. So you just call the counter whenever you encounter the word and you keep incrementing the counter. So that is something which it can very well keep it as a global thing. And this is generally done when the number of or the statistics which you want or the analysis which you want to perform is like very simple. So in such cases, you can get done with a map only job without having to go for a MapReduce job, because in MapReduce job, you know that there is a data transfer cost associated between the map and reduce changes. Finally, we also have this thing called as a MapReduce join. Okay, so the final 2 things are essentially about how to implement the join operation using MapReduce. So the join operation is perhaps, as you know, the most important operation in SQL. So you have 2 data sets. Most of the time you may have to join these 2 data sets based on a particular attribute. So MapReduce can also do joins, and it can do it in multiple ways. Okay, so you can do it using both map as well as reduce, which is what we covered here. And then there is a very nice way to do it using a map side join only. Okay, which won't involve a reducer, and that is done by using what is known as a distributed cache. So, but remember that the map only map side join is applicable only if you have a small table and a large table and you want to join these. Okay, in some sense, if you have a lookup table which is small in size, then what happens is you can actually send the smaller table to each of the individual nodes, and that is what we refer to as a distributed cache. Then you can actually split the larger table and perform the join on each of these nodes, because the smaller table is existing on all the nodes, so you can actually perform a join. However, if both the tables are big, then you may not be able to send a complete table into all the nodes. So in that cases, you may have to stick to the MapReduce join. And finally, we show how to monitor a job using the Hue interface. So these are certain things which have been covered in this particular session of the module. And then finally, in MapReduce Programming 3, we have given you some additional demonstrations which compute averages, and there are a few programs which involve Aadhaar data. And in particular, we show you how to chain MapReduce jobs. Okay, this is also an important thing. That is, you can create some kind of a workflow using MapReduce, wherein the output of the first job goes as the input to the second job. You can have a third job where the output of the second job goes as the input to the third job, and so on and so forth. You can build a chain. And similarly, you can have deduplication and all these. So these are some additional demonstrations, and that's it. So when I told you that you can create a simple workflow using MapReduce, why I call it a simple is because using only MapReduce, you cannot have a meaningful workflow wherein, let's say you want to have two jobs to run in parallel, and you want to join the output of these 2 jobs. Okay, this is a very common task which you will have to perform as you will see later. So I have 2 jobs. I want both of them to run in parallel, and then I want to join these 2, the output of these 2 jobs. Now, of course, you can do this sequentially. That is, you can let the first job run, and then you can run the second job and do things like that. But to automate the entire thing is something which the simple MapReduce framework doesn't allow you. So in such cases, essentially when we want to make or to develop really complex workflows, then that is when we will have to go for workflow managers like Oozy and all, which you will see later. So Oozy essentially allows you to create workflows where you can have multiple jobs running in parallel, and you can create joins. In fact, you can even create decision nodes wherein if something is not complete, then the other doesn't start, and so on and so forth. So all those things will be taken care of. In fact, a PIG, which is an abstraction built on top of MapReduce. One of the major motivations of building PIG was to also create some kind of a workflow using several MapReduce jobs. So you need not have to. PIG allows you to actually write some high-level code, and it essentially creates MapReduce jobs and runs them, and completes the workflow. So there are a lot of such things which came step by step. So all these things will be covered later on in the program. So as you can see, there's a lot of content which has been covered in this particular module. It's quite intensive. It involves a lot of coding. Okay, I strongly recommend each one of you to run the programs that the code which we have provided to you to tweak the problem and try to change the code and see how the results change and so on and so forth. Apart from this, we also have several coding questions which have been provided to you. It is scattered across the sessions. So in short, it means that you need to really invest a lot of time in this module. So I really recommend each one of you to start early. If you haven't started already, please start as soon as possible, and try to do or practice as much as possible, and only then you can actually proceed further and go for the next thing, which will be the Savan MapReduce project. Okay, so I think I'll just go through that part also. The Savan MapReduce project. So the Savan MapReduce project, we will have a separate session for a detailed session explaining about the MapReduce project. But here I will just quickly try to tell you what is being expected. So you will be given a huge data set. Okay, it's a huge data set, and it has been hosted on S3. It's around 44 gigabytes. It's 1 month of stream records from Savan, and you are asked to find out what are the trending songs. Okay, so this is a problem statement that has been given to you. You are also given Savan's trending songs for this period, so you can actually compare your output with Savan's output and see what is the overlap and so on. And the whole idea so of course there are two objectives. One is of course to test your MapReduce skills, and secondly, this problem, the project which has been given to you, it is special because you will be deploying it entirely on cloud. By what I mean by deploying it on cloud is not just that you are going to run your MapReduce program on cloud. That is definitely for sure. But apart from that, even the data, as you know, MapReduce, so far, whatever you learn, you will actually put the data on HDFS, and MapReduce will process the data on HDFS. But in the project, we will show you how you can actually start processing without having to copy your data on HDFS. So the data will lie on S3. We will use something known as S3 connector, which allows your MapReduce program to fetch the data from S3. Okay, it will process it, and you can actually put the output also back on another bucket on S3 itself. Okay, so these are things which in fact the industry is slowly moving towards. That is, S3 is already a very reliable storage service. So why you actually download it on HDFS and then process it? Rather, I could very well fetch the data from S3. The MapReduce program can fetch the data from S3, process it, put it back on S3. Okay, so this part is also covered through the project. So it's a fairly challenging project since it involves a lot of data, and hence there will be a lot of debugging which you may have to do, because the scale at which the data processing is done here. So several unexpected errors may come in and so on. So only if you are like very confident in programming, then you can go one step ahead and do the debugging. So that is the reason. why we strongly recommend you to complete the module and start looking into the problem statement and others as well for the project. So yeah, so that's it as far as the overall. I wanted to run you through the module and the project. Now perhaps we can discuss around if there are any specific issues or something. We can. Are there any questions on the?
Yeah, you can take your time and unmute yourselves and ask your questions in case you have any. Oh, okay. No questions at all. Very interesting. All right. Great job then, Sandeep. Gone over the concept so thoroughly. None of the participants have any questions for you as of right now. In that case, I think we'll wrap up the session unless anyone has any questions that they want to jump on. Now is a great chance to. All right then.
Yeah, so if there are no questions, I would just briefly talk about what are some of the limit. I already told you one limitation of pure MapReduce, which is it doesn't give you any feature which allows you to build complex workflows. That is one thing. And of course, another major limitation of Hadoop MapReduce is that everything is based on disk. So you have a mapper, you write the intermediate output on disk, and the reducer then fetches it from disk and again writes it back to disk. So if you want to change several MapReduce jobs, you know what is the latencies which is caused by all this input output on disk, because disk fetching is generally much slower than fetching from memory, right? So this is something which is a major limitation of Hadoop MapReduce, and a big breakthrough as such in this field was the introduction of Spark. So what essentially Spark did is it made all this, or it's not so simple as it is, that is to turn everything from disk onto memory. They built a nice system which actually allows you to do everything in memory and using and even there it provides you fault tolerance. So of course the major challenge here, or the reason why Hadoop MapReduce does everything on disk, is because it wants to persist the output, right? It wants to so that is a major reason why everything is put on disk. One is you cannot fit everything in memory. That is the number one reason. And second thing is you want to persist on disk. So what Spark does is Spark tries to fit things into memory, okay, as much as possible. A reason for that is also because these days memory also has become much cheaper, and the size of memory which is also generally available in commodity hardware has also increased. So if you have like 100 nodes each with 16 GB of RAM, then you're looking at 1600 gigabytes, right? So that is something which allows you to perform in-memory processing. But even there, if you think about it, in memory, you cannot persist something. You are not writing on a disk. In a disk only you can persist it. Memory is volatile. So how can you think about providing fault tolerance on Spark? So that is where Spark came up with a nice way of building up something called as RTD and RDD with lineage graph. So essentially, in layman's terms, what it does is like it builds a lineage graph. That is, if there is like step 1, step 2, step 3, step 4, for each operation, it will maintain that particular graph. That this, I did step 1, I did step 2, I did step 3, I did step 4, and I reached there. So even if that final output after step 4 is gone, that is the node hosting that is gone, you still have this graph, the lineage graph, and you can actually go back. That is, you can start with the input and you know, I only need to apply step 1, 2, 3, 4, and I will get wherever I reached here. So this was what Spark essentially did. But even over there, the transformation which you perform on Spark are still very much like MapReduce. By MapReduce, what I mean is like the map and the reduce construct. So something which you will really have to keep in your mind is the technology or the framework may change over time. That is, you had Google, which came up with MapReduce a decade or so earlier, and everything was fine for that. It solved their problem. MapReduce, that is, which was majorly around computing page rank and so on. So it solved that problem, but over time, of course, we wanted more performance. So the framework shifted. We have a better framework now, which is Spark. But the paradigm, that is algorithm design framework of using map and reduce to compute or to process something in a distributed fashion, that is fundamental. So that is not going to change. At least as such, no other constructs are there which does things so nicely. So that will be there as an underlying part of each and every framework. Only the framework or the technology may improve over time. So that is something which I would like to tell you about, and you get a very good idea about how improved you get the performance with Spark when compared to MapReduce as a part of the Spark assignment which will be given to you. So in fact, it's a proof of concept where you will write the same program, implement the same program, run it on Pig, which is essentially MapReduce. All that you are doing is abstracting MapReduce, and then you will run the same program on Spark, okay, and you will be actually comparing their performance. You will see that there is a noticeable improvement with respect to Spark and compared to MapReduce. At the same time, it's not like Spark has come and it has replaced everything which involved MapReduce. That is far from the truth. There are still several things which does involve MapReduce. So for example, when we go on to ETL, you have things like Scoop, which is essentially like it's a data ingestion tool which picks, which is used to ingesting the data from traditional RDBMS and to put it onto Hadoop. So Scoop is also an abstraction on top of MapReduce. Essentially what Scoop does is it allows you to write high-level commands, and Scoop converts it into MapReduce programs and runs them, and it will fetch data and put it onto your table onto Hadoop. Similarly, Hive, for that matter, Hive queries, whenever you write, it essentially converts Hive queries into MapReduce, and it again process. It's used to analyze data. So these are certain things. So the reason why these are again still important or still relevant is because all the APIs which are presently supported by Spark, they are not stable for everything. There are a good set of APIs which are stable, especially looking forward to the last course which you will be learning. It is using machine learning. Okay, machine learning, Spark provides you with a library called as MLlib, and that is pretty mature, it is pretty stable. So hence you will see that machine learning, most of the applications these days are done by Spark, but traditional ETL and data warehousing is still things which are it's still happening in the industry, and the features which are provided, certain features which are provided by Hadoop and MapReduce for that matter, they are very, very stable. They are still very much in use. So that's what I would like to tell. And something which we really wanted to reduce, we wanted to give you even a project based on MapReduce, was that we strongly believe that if you are able to code at such a low level using the basic map and reduce, then it gives you a very strong idea about how these two constructs can be used to solve challenging problems. So for example, if you look at the joining, performing the join operation using MapReduce, it's a very nice, clever way to use map and reduce to perform a join. So such things, such a flavor you won't get if you go directly to Spark or Hive or Pig, because over there you have certain high-level commands which you can directly use and it will fetch the results for you. But in MapReduce, if you want to do the same thing, you will have to sit and code, write the map method, write the reduce method, think carefully if you can actually implement a very clever combiner, right? And see if you can actually get a partitioner and try to distribute the data. And all these things, it becomes very clear, you get a very good understanding of the MapReduce paradigm by actually implementing it using on Hadoop MapReduce. So it's a very important module from several perspectives, and hence, again the same thing. I know I'm repeating myself. Please go through the module, try to practice as much as possible, even look outside for exercises and see if you can actually write a MapReduce program for doing some challenging tasks and so on.
Hi Sandeep, this is Nitin here. Can you hear me?
Yeah, Nitin, yeah.
See, I have one basic question. I'm sorry I joined a little late. See, in the distribution system, we talk about the different kind of nodes, right, which is performing parallel processing, etc. When I go to the AWS Amazon services, I configure one machine, and then I can't relate the different kind of nodes. Do I need to configure a different machine just to have the architecture of distribution? How it will execute parallelly the MapReduce task? Yeah.
Okay. So here, of course, if you want to get a real understanding, or if you want to really see how the distributed thing works, of course you will have to go for a multi-node cluster and so on, but you will still get a fair understanding of how this distributed processing works by even on a single node cluster. So the reason why we are restricting ourselves to a single node cluster is, one is because most of the data processing that we'll be doing, a single node cluster does the job for us, okay? And secondly, it is like when you go to AWS and you want to configure a multi-node, then of course there is a cost associated with and so forth. But in one of the future modules, you will actually be even getting a flavor of having a multi-node cluster. Okay, but for at least for this module, we get all of our tasks done using a single node cluster, and I will tell you exactly how you will. You can see how the parallel processing works. So when you go to resource manager, so this is something which is explained in the job monitoring thing. If you look at your module, then there is a particular thing which involves job monitoring. I think it's a part of MapReduce Programming 2, that session. In that session, we have showed you how you can monitor a job using the Cloudera Manager interface. So in Cloudera Manager, you can go and there are web UIs for the resource manager. There's a web UI for job history server and so on. So if you go to resource manager's web UI, you can actually see that how many containers are running, how much memory is being used by each container, how many cores are being used by each container, and so on. So if you try to relate, then you know that very well that starting from Hadoop 2, everything is in the form of containers. So you have, let's say, each container has 2 gigs of RAM and 1 core each. Okay, so you can very well monitor your job there, that as the job is progressing, how many containers are being spawned, how much memory is being used, how many cores are being used. You even can tweak your settings on your Hadoop configurant, that is Cloudera Manager, about how much memory, what is the maximum memory that it can use, and so on and so forth. Although I do not recommend you to do it as per we have provided you a document on what is the settings that you need to do. Even if you want to try out something, ensure that after trying out, you get back to your original setting. Because generally sometimes what happens is if you keep it too less, then sometimes the job doesn't start. And if you keep it too high, then sometimes there is not enough memory for the other applications to run on your EC2 instance and so on. So in short, what I'm saying is, even with a single node, you can very well see the various containers in action, how MapReduce is actually, or the framework is actually doing this. And you can even see what are the number of map tasks, what are the number of reduce tasks. All these information you will be able to see even on a single node. So you're not losing out on a lot of things, except for probably you won't be able to see real time if what happens when a node fails. Okay, so that part about node failure and how Hadoop accounts for node failures, we will definitely show you in the later module. I think that comes as part of Kafka, where we will show exactly what happens when a node fails and how Hadoop takes care of that.
Thanks, Sandeep, for the answer.
Yeah.
Hey, Sandeep, this is Sudhakar. Hi.
Hey, hi, Sudhakar.
Hey, I have a question regarding the disk space management in Cloudera itself. So
okay.
Suppose right now the VM that we created in cloud, suppose it has 50 GB of hard disk.
Yeah.
But when we, I think in the documentation and when the CLI for this VM, the document contains some of the commands which gives you the space information about the HDFS. I think memory, right? Now that memory, I think what I saw was around 2 more than what usually you will see. How? I mean, my question is directly to how is Cloudera internally managing the HDFS? How does the memory from the local one node cluster it takes? And how does it allocate to its data nodes or maybe the name node in it? Am I audible? Sandeep?
Oh, I see. So what your question is something like... Oh, I see. Is it? Are you able to hear?
I am actually, you're breaking up, but right now I just fine.
Okay. Yeah, so I'm just trying to get your question right. So your question is like, of the volume, EPS volume that we have, which is 50 gigabytes, how Cloudera is actually giving the disk space to the node manager and not the node manager, the name node and the data node, right?
Correct. So, I mean, for the data nodes, for the name nodes, or maybe the standalone node, standby node, the amount of the number of nodes that we have in the cluster that we usually in architecture, how does that happen, and on what basis does that gets decided?
So there is a default, I would say, a percentage sharing by which it is being. So in general, what happens is that when we install or generally whatever happens is that this space as such is generally not an issue, and hence the configuration which you will see on your Cloudera manager will more or less always involve giving or restricting the memory available for node, name node, and data node, and all these what you say, the daemons which you want to run on your system, right? So so the reason being that, as you may notice that the data storage, the data storage is done by the data nodes, and these are the ones which require the bulk of the space. So I'm very sure you actually get access to almost your entire disk space for the data nodes. Now, however, the name node requires a fair amount of memory because it has to keep all the metadata, and it has to keep regularly updating this. So there is, in fact, you will get a prompt when you log into Cloudera Manager about it will actually prompt you that the memory which you have allocated for the name node is less. So there is a figure which it shows that if you have so many gigabytes or so many number of name nodes, then you should have so many gigabytes of memory allocated for the data node, and so many gigabytes of memory allocated for the name node. So there is a calculation, and most of the calculation is generally with regard to the memory allocation, because as I told you, when you go to a multi-node cluster, of course there is no issue, because you will generally have a dedicated cluster or a dedicated node which runs a name node, and hence you need not have to share any resources. But otherwise, when you are running all the daemons on the same node, then there is a clash of what memory I should actually allocate for each of the daemons. So it is only a problem with the memory and not much with regards to the disk space, because as far as the disk space is concerned, I'm pretty sure, I will have to check it again though, that most of the disk space should be available for the data nodes.
All right.
Yeah.
And for the fact, right now as we are talking about single node clusters, so all these name nodes, when we talk about them, these are not, I would not consider them as a node. I would consider them as services running on a single VM.
Yeah.
Right?
Yeah.
If I talk about real cluster, then each component should have its own VM, if I'm not wrong.
Exactly. You will have Hadoop installed on each of these things.
Hadoop installed on each of these things? I didn't get that.
So you will have the name node service running on whatever is your master node, right? And you will have the data node service running on your slave nodes. So as you told, you are perfectly right. These are services which are running on the nodes, right? So yeah.
If I talk from the point of view Cloudera installation, Cloudera distribution,
okay.
Right?
Yeah.
So when we installed Cloudera, it gave us the data nodes, it gave us those services on a single node.
Correct.
But when I talk from the perspective of that, if I want to separate the actual nodes, actual VMs, how does then Cloudera manages that? Because right now it is doing all the services installed on the same node, whether it is a master service or slave service.
Yeah. So if you go to Cloudera Manager, you actually have the option of adding nodes to your cluster. So it's always starting with a single node wherein you will install Cloudera Manager, and then you will add nodes to your cluster. So as you keep adding nodes, Cloudera will actually distribute the required parcels to the other nodes. So thereby creating a synchronous cluster.
Okay. And it also gives you the ability to choose which one to make a master and which one to make slave?
Yeah. So by default, it will be obviously the first guy who is the master.
Okay.
But yeah, you of course have the option of assigning the master to as another node rather than what you have chosen right in the beginning.
Alright.
Yeah.
Sandeep, this is Mahesh here.
Yeah. Hi, Mahesh.
Yeah, actually, I tried adding a host, different host onto the Hadoop cluster.
Okay.
But I faced a lot of issues. I tried a lot, but I couldn't do it. Can we get any example or how we need to add it?
Okay, so if I'm not, what your question is like, were you trying to create a multi-node cluster?
In a same cluster, I am trying to add a host so that I want to add a data node, separate data node to that.
Yeah. Okay, so yeah, regarding this part, what I would say is like, of course, you can try it out. You can create a multi-node cluster and try the things out. But I would also recommend you to try it and perhaps you can terminate the instance because of that you don't exhaust your balance because of the EBS volume, because you will have a lot of data processing running on. Regarding how to set up the things, we can have a separate kind of a session with our big data admin who will be able to guide you with this process. So maybe you can get in touch with Anirudh and Avdesh, who is our big data admin. He can either guide you or he can provide you with the required resources.
Okay, thank you. Yeah. I'll send an email to Anirudh.
Yeah, sure.
Sandeep, Sudhakar this side. One more question. This is regarding the module, the project. So when I was watching the video, you were using a 7 project jar file. When you ran that command with the help of S3 bucket, taking the input and output, what exactly that jar file was doing? I mean, was it processing the data, taking the input from S3 bucket and putting the output as? What exactly that jar file was doing?
Yeah, it was actually the jar file which you will run for the MapReduce project. It will essentially take the data, or the data is residing on an S3 bucket, and what the file does is it's a simple MapReduce job. The only difference here is that the source of data is S3 and not your HDFS, and it processes it and it puts the data back on another S3 bucket. So now HDFS is not allowed, but other than that, it is a simple MapReduce job.
Okay. I'm sorry I'm asking this question because I haven't, made much progress in the module. The program that we'll make, will we be implementing the map and reduce operation ourselves, or will we be using APIs of map and reduce and use them to implement the logic?
No. So see, it is like you will in the module also you will have to write your own map and the reduce methods, right? So yeah, so it's like throughout the module, even for the project, you will have to write your own map and reduce methods, and you will have to pack it as a jar file, and you will have to run it on the cluster.
Okay, understood.
Yeah.
I think that's all of the questions that we've had so far. So I think we can go ahead and
I think we can.
now. If there are any further questions, you can always email them to me, and I'll make sure that Sandeep reads them and gives me his take on that. Thank you everyone for joining us. Thank you, Sandeep, for taking such a wonderful session. And good night. Thanks.
Thank you.